All right, this is our first video lesson for section 6.6, which is a section on solving polynomial equations. In this first video, we're just going to be looking at some new factoring techniques that we can use on polynomials. And then in our second video, we'll actually use those factoring techniques to solve some equations, okay? So the first technique we're going to look at is called grouping. And grouping is going to be a technique you want to use primarily on a polynomial that has 4 terms to it, okay? And the idea here behind grouping is that while all 4 terms don't have a greatest common factor associated with them, you can group a couple of the terms together that do have a common factor, okay? So notice I already have an example worked out here. X cubed minus x squared minus 7x plus 7, that's our polynomial. Notice there is no GCF between all 4 terms, okay? But if I group the first 2 terms together and then the second 2 terms together, I'm able to pull out some common factors between each of those pairs, okay? So notice x cubed minus x squared, I'm pulling out an x squared from each of those, which then leaves me with x minus 1. And then negative 7x plus 7, from both of those terms, I'm factoring out a GCF of negative 7, which also leaves me with x minus 1. And it's no coincidence that I end up with x minus 1 left over both times, okay? That's what I need to happen in order for me to have grouping work here, okay? So notice what we've done to go from that middle line down to the final factored form, okay? What we've done is we've essentially taken the x squared and the negative 7, and we've put those together into its own factor, and then x minus 1 we've written one time. And notice technically, algebraically, what you're doing there is you're factoring out x minus 1 as a GCF from both of those expressions, okay? So now let's apply it to a couple examples of our own. The first example here, I'll start by grouping the first 2 terms together as well as the second 2. Now think about what these first 2 terms have in common. They have a 3a squared in common. When I pull that out, I would be left with 2a minus 3b. And then what do these 2 terms have in common? Well, they have a positive 2b in common. So when I pull it out, I need to put a sign in front of it. So make sure, since it's positive, you're going to put a plus sign. And then what's left over is 2a minus 3b. Now, once again, it is not a coincidence that these are the same, okay? I need those to be the same so that I can now write as follows. I'll have one factor of 3a squared plus 2b, and then I will have a second factor of 2a minus 3b, okay? So there's the complete factorization for that original polynomial that had 4 terms to it, all right? Second example, again, notice there's 4 terms. There is no common factor between all 4 of them, okay? So I'm going to group the first 2 together as well as the last 2. X squared plus 5x squared, they have an x squared in common. If I factor that out, I would be left with x plus 5. And then negative x minus 5 right here, you might be tempted to say that they don't have anything in common, but you can always factor out a 1 or a negative 1 from multiple terms, okay? So in this case, it's going to be beneficial for me to factor out a negative 1 so that what's left over is also x plus 5, making, again, these 2 identical, okay? All right, now that then allows me to go to x squared minus 1 as one factor, and then x plus 5 as a second factor, okay? Now you might be tempted to stop there, but there is one more factoring technique that can actually be used here. What we need to observe now is that x squared minus 1, that is a difference of two perfect squares. And recall that that factors into conjugate pairs. So x squared minus 1 is going to become x plus 1, x minus 1. And then you can carry down the x plus 5. So this would be considered the complete factored form of that original polynomial. Okay? All right, so the next factoring technique we're going to look at is based on sum or difference of two perfect cubes pattern. Okay? So again, this is a very specific technique. It only works when you have two perfect cubes added together, or two perfect cubes, one being subtracted from the other. Okay, and we have, in a sense, a formula that can be used for each of these scenarios. Okay, so the formulas are shown in red boxes here. The rule for the sum of cubes, if you have a cubed plus b cubed, so obviously a cubed is a perfect cube, b cubed is a perfect cube, they're being added together. So this is a sum of cubes. Notice the factorization for that will be a binomial multiplied by a trinomial. The binomial would be a plus b, where a and b are the cube roots of your a cubed and your b cubed terms. Okay, and then look at your trinomial right here. So once you know the cube roots of a cubed and b cubed, that gives you a and b. You simply are going to square a to give you the first term of that trinomial. You're going to multiply a and b together to give you the second term, and then notice there's a subtraction in front of that. And then to give you the final term, you're going to square b. All right. For the difference of cubes over on the right-hand side here, notice it's essentially the same pattern. A cubed minus b cubed, it will factor to a minus b multiplied by a squared plus ab plus b squared. So really the only difference here is some of the signs on the terms, okay? So again, these are two formulas that you need to essentially memorize. And what you can do to help memorize those is utilize, I have a little acronym that's going to help memorize the sum or the signs on the different terms here, okay? So the acronym is SOAP, S-O-A-P. The S stands for same, and here's what that means, okay? In your binomial factor, notice that the sign right here is the same as the original sign, and that applies over on the difference of cubes as well. That's the same as right here, okay? Now the O and the AP correspond to the signs within the quadratic factor, okay? So O stands for opposite. So what that means is that this sign right here is always the opposite of the original sign. So notice these are opposites. And then same here, these are opposites. And then the A and the P, they go together. A stands for always, P stands for positive. So AP means always positive, and that just means this last term here is always going to be positive, okay? So that can help you just, again, remember the signs of your terms in your different factors, okay? So look at the example that's worked out on the left-hand side. 8 plus 125z cubed, we're trying to factor that. So the first thing you're going to do is you're going to find a, which is the cube root of 8, or 2. And then you're going to find b, which is the cube root of 125z cubed, or 5z. And then you just simply plug in those values of a and b into the formula that's in the red box there. and then you simplify. Okay. Notice for the example on the right-hand side, the difference of cubes, 64 minus 125v cubed. It's essentially the same approach. Find the cube root of 64, find the cube root of 125v cubed, and plug those into your formula for a and b, and then simplify. All right, so let's apply the formulas to the following examples as well. X cubed plus 216, that's a sum of two perfect cubes. So if I find the cube root of x cubed, that is of course x, then I find the cube root of 216, that is 6. Okay, so the factorization is going to have a binomial factor of just x plus 6. Okay, and then the trinomial is going to start with x raised to the second power minus, notice I'm using the opposite sign from the original right here, so minus the product of 6 and x, then plus, for always positive, the square of 6, so that's 36. Okay, and then that is as factored as you get. All right. Second example, this is a difference of perfect cubes. So the cube root of 64x to the 6th, that would be 4x squared. Okay, and then the cube root of y to the 6th is of course y squared. All right, so plugging 4x squared and y squared in for a and b in the formula for the difference of cubes, that's going to lead you to a binomial factor of 4x squared minus y squared. Okay, and then you're going to have a trinomial. The first term of the trinomial would come from 4x squared being raised to the second power. So that's 16x to the 4th. Then you're going to need a plus sign for the opposite of the original. You need the product of 4x squared and y squared. Then plus sign for always positive. And now you need the square of y squared, which is y to the 4th. Okay. Now, you might be tempted on this one to stop, but similar to one of our examples in grouping, what we now want to notice is that 4x squared minus y squared, that is a difference of perfect squares. Okay. And again, those factor to conjugate pairs. So that's going to become 2x y times 2x minus y. And then you can just carry down the trinomial. Okay. There's our complete factorization. All right. Final factoring technique to look at involves a quadratic pattern. All right. We are used to factoring quadratic trinomials of this form, ax squared plus bx plus c, right? And there are other polynomials, specifically trinomials, that their makeup is very similar to this, and we call them quadratic patterns, okay? So a trinomial follows a quadratic pattern if the middle variable squared equals the first term's variable. So the middle variable here is x. If I square that, I get x squared, right? And then, of course, you need a constant right here for this to be considered a quadratic pattern, okay? So notice the example in the box here. X to the 4th minus 11x squared plus 30. That trinomial follows a quadratic pattern because you have a constant of 30, and then if I take that middle variable of x squared and I square it, I end up with x to the 4th, okay? So that means that if this is factorable, I can take a very similar approach on how I factor a regular quadratic trinomial, okay? Notice it factors to two binomials, right? X squared minus 5 and x squared minus 6. And really the only difference on those factors is they both have to begin with x squareds, okay? Those x squareds are what's going to give you x to the fourth in the trinomial when you multiply this out, okay? Now, the -5 and the -6, they're responsible for two things, okay? So notice -5 times -6 will multiply to the constant of 30. And then when you do the outside and inside parts of FOIL, -6x squared and -5x squared will combine to give you the -11x squared. That's the middle term of the trinomial, okay? So let's apply this, same type of pattern to the two examples below, all right? In A, that is a quadratic pattern because we have a constant of -15. X cubed, if I were to square that, I end up with x to the sixth, okay? So if this factors, I know the two factors, they're going to need to begin with a 2x cubed and an x cubed. That's the only way you're going to be able to create the 2x to the sixth power, all right? And then the numbers that I follow each of those up with, first and foremost, they're going to have to multiply to -15. And then outside and inside parts of FOIL are going to have to lead me to the 7x cubed. So the proper factors would be a -3 there and a +5 here. Okay. Now you can just double check that. If you did the first part of FOIL, you would get 2x to the sixth. Outside part would get 10x cubed. Inside part, -3x cubed. And then last part, -15. Notice, of course, those combine to the 7x cubed. So we're good here. All right. Second example there. Again, notice this is a quadratic pattern because you have a constant of 100. If I square x squared, I end up with x to the fourth. So if this factors, both factors are going to have to begin with x squareds. And then I'm going to need to follow those up with two numbers that multiply to 100. What it's going to end up being is a -25 and a -4. Notice, again, if I do outside and inside parts of FOIL, that'll lead me to the middle term of the trinomial -29x squared. Okay. Now, don't stop here. Recognize that both of these factors can factor further. They're both difference of two perfect squares, so they become x plus 5 times x minus 5, x plus 2 times x minus 2. There's your complete factored form.